Imagine you are building a simple control system where a light should only turn on when someone presses a switch, like how a lamp lights up when you press its button. In this experiment, we will use an ESP32 microcontroller, a push button, and an LED to replicate this everyday situation. The push button acts as the input and the LED acts as the output. By wiring them together and writing a short program, we can demonstrate how pressing the button sends a signal to the ESP32, which then turns on the LED. When the button is released, the LED turns off. This simple setup introduces us to the concept of digital input and output, the foundation of how microcontrollers interact with the real world in smart devices. Open Wokwi in your browser and click Start a new project. From the left toolbar, drag a breadboard into the workspace to make it easier to connect parts. Next, drag an LED and place it on the breadboard so that each leg sits in a different row. The longer leg is the anode and should be connected toward the resistor, while the shorter leg is the cathode and will be connected to ground. Drag a resistor and connect one side of it to the anode of the LED. Make sure to change the resistor's value to 220 ohms. Start by connecting the GND or ground pin of the ESP32 to the breadboard's ground rail. Place the LED on the breadboard with the short leg, cathode, going directly to the ground rail. Now connect a 220 ohms resistor to the long leg, anode, of the LED, and from the other side of that resistor, run a jumper wire to GPIO 14 on the ESP32. This ensures the current flows from the ESP32 pin through the resistor, then through the LED, and finally to ground. Next, mount the push button so that it bridges the center gap of the breadboard. Connect one leg of the button to GPIO 12 and the opposite diagonal leg to the ground rail. With this wiring, and using pin mode, button pin, input pull-up in your code, the input pin will normally read high. When the button is pressed, GPIO 12 is pulled low, which your code interprets as a button press, toggling the LED state. Before running the simulation, make sure the resistor value is set to 220 ohms to properly limit the current through the LED and protect it. This line includes the Arduino core library, which gives the ESP32 access to standard Arduino functions like pin mode, digital read, and digital write. Without it, the compiler may not recognize these functions when building for ESP32. These two lines create constants, giving the names LED pin and button pin to GPIO 14 and GPIO 12, respectively. This makes the code more readable and easier to change if you want to use different pins later. The setup function runs once when the ESP32 powers up or resets. It's used to configure pins and initialize serial communication or peripherals. This sets GPIO 14, the LED pin, as an output, meaning the ESP32 can drive the pin high, supply voltage, or low, ground, to control the LED. This configures GPIO 12 as an input with an internal pull-up resistor. That means when the button is not pressed, the pin will naturally read high. When the button is pressed, it connects the pin to GND, making it read low. This closes the setup function. The loop function runs continuously after setup finishes. This is where the main logic of your program lives. This reads the logic level of GPIO 12. If the button is not pressed, it will return high. If pressed, it will return low. The result is stored in the variable button state. This checks whether the button is currently pressed. Because of the pull-up configuration, pressed for low. If the button is pressed, this drives GPIO 14 high, sending voltage to the LED, which makes it turn on. This is the else condition. If the button is not pressed, meaning the pin is high, then execute the next statement. If the button is not pressed, GPIO 14 is driven low, cutting power to the LED and turning it off. These closing braces end the if statement and the loop function. The loop then repeats indefinitely, constantly checking the button and updating the LED. This code configures one pin as an output for the LED and another pin as an input for the push button with a pull-up resistor. It continuously checks the button's state. If pressed, the LED turns on. If released, the LED turns off. We're going to modify the code so that the LED acts like a toggle switch. Right now, the LED only stays on while the button is pressed, but with a toggle, one press will turn it on and the next press will turn it off. To make this work, we'll add a variable to keep track of the LED state and update it only when we detect a valid button press. Because push buttons can be noisy and may cause multiple false triggers, we'll also include a simple debounce mechanism using the millis function to ignore very quick, repeated signals. In this new code, we declare an integer LED state to store whether the LED is currently on or off, and a variable last button state to remember the button's previous state. Inside the loop, we check if the button has just transitioned from high to low, meaning it was pressed. When that happens, we flip the value of LED state using the no-t operator and then update the LED with digital write. With the debounce delay added, the LED will reliably switch on with one press and then off with the next. This small change demonstrates how microcontrollers can use simple logic and state variables to create toggle-style controls that are common in real devices like lamps, fans, and power buttons. Thank you so much for following along with this tutorial. I truly appreciate your time and dedication to learning. Don't forget to like this video if it helped you, share it with others who might benefit, and subscribe for more tutorials. See you in the next video, where we'll continue exploring exciting projects with the ESP32. Until then, happy learning and happy building.